Yes. So we're going to be having some spotlight talks right now. So Martina will share her screen with the pre-recorded video from the people with contributed work. So we'll play the video and then we'll have around 1 minute after each video for a question. So for those, please either type it in the Zoom or Slido, or if you're willing, you can walk up here until we fix the microphone issue. But anyway, I think we should move on to the next speaker. And I see the next speaker is on the Zoom call. Okay, good. So let's play the video.
Hello, everyone. My name is Mingrui. It's a great honor for me to present our work, Shape Control of Deformable Linear Objects with Offline and Online Learning of Local Linear Deformation Models. In this work, we consider the shape control of deformable linear objects, just like these previous works shown in the video. The task objective is to manipulate the DLO to the desired shape. For control, the key challenge is to obtain the exact deformation models. In other words, how the robot motion affects the DLO shape. The previous methods to obtain the deformation model can be summarized as follows. First, using analytical models. However, they are just approximate model and require accurate DLO parameters. As a result, data-driven methods are more practical. They can be further divided into offline and online methods. In offline methods, the most common one is to offline learn a nonlinear global forward kinematics model. However, the model training is usually data inefficient, and they may get into trouble when manipulating a new DLO. The online methods usually online update a local Jacobian metric. These methods can be applied on any new objects, but they are only effective in local configuration and less accurate. To address this issue, we propose a new method which learns the deformation model in a coupled offline and online manner. The model is first trained based on randomly collected data in the offline phase, then seamlessly migrated to the online phase as an initial estimation, and further updated while achieving the shape control tasks. The advantage is that it can allow for both more accurate modeling via offline learning and adaptation to new DLOs via online learning. As for the formulation of the deformation model, we use the local Jacobian in a global way. Here, our Jacobian model is not just a metric, but a mapping from the state to the Jacobian metric. The advantages are that it is both globally effective and more data efficient because it implies a strong linear prior. We proved the reasonability of this formulation under the quasi-static assumption. We use an RBFN to approximate the Jacobian model. We also propose a proper relative state representation as a network input. During the actual manipulation, the weight of the RBFN is further updated to compensate for offline modeling errors. We also analyze the stability of the closed-loop system using the Lyapunov method. We build both 2D and 3D simulation environment. The offline model is trained using only simulation data. First, we compare our Jacobian model with FKM. We test their offline model accuracy on a certain DLO. The results show that our model can achieve more accurate predictions with less training data. We also validate the proposed relative state input. The results show that it can enable the offline model to have better generalization ability on new DLO. Here we show some shape control results in the real world. It has shown that our method can achieve better shape control results than the previous works. Here are more cases accomplished using our method. In summary, our method is more stable and more precise. In conclusion, we propose a new scheme for shape control of DLOs. combining both offline and online model learning. We conduct both simulation and real-world experiments to show the superiority of our method. Recently, we have just submitted a journal version of this work, in which we propose new model modifications and training strategies, a new optimization-based controller, a new robust online model updating law, and more detailed simulations and experiments such as dual-arm 2D ship control, dual-arm 3D ship control, some potential application cases, and a demo for obstacle avoidance. That's all. Thanks for listening.
Hi.
Oh, do you have any question for the speaker? Well, I mean, I have a question if that's okay. So I'm actually curious. You talked about offline and online learning. So I'm curious, how far can we go with just offline learning? Like, do you need the online learning, or how important is that stage?
Nowadays, I think, thank you for your question. I think nowadays both offline phase and online phase are important because I think all simulators for the deformable objects are not perfect now, so there are a huge reality gap. That is why we think online model adaptation is very important. But if we have only online phase, the limited online data cannot ensure accurate model learning. Okay, thank you.
Okay, so maybe we should move on to the next video. And Mingrui here?
Yes. Thank you, Mingrui.
Here?
Yeah, I mean, if they're in the audience, they can come up here, sit here watching the video, and then answer questions.
Okay,
Hi everyone, I'm Guillem.
Yeah.
And in this workshop, I'm going to present our work entitled an SE3-based formulation of the shape servoing problem. A general approach to solve manipulation tasks is shape servoing, also called shape control. The goal of shape servoing is to provide commands to a robotic manipulator so that it deforms a deformable object autonomously to give it a desired shape. In the literature, there are model-based and model-free approaches. Model-free ones operate in closed loop. The desired shape is given as input and is compared to the current shape of the object. With this, we obtain a shape error that the control law transforms into robot commands. Once these commands are executed, we obtain a new shape of the object from which we extract features of interest to close the loop. Different solutions have been developed for this, but a very interesting one is to use position of points in space, since this provides a direct way to define the target from the task objective. So in this approach, that I will call position-based servoing, the features in the control loop are defined by the three components of points on the object. We note them Y and their desired position YD. Moreover, independent grippers grasp the object rigidly and their pose is noted Z. Then, if the system is quasi-static, we can linearize around the current configuration to obtain a relation where a Jacobian relates gripper motions to feature motions. This matrix is called the shape Jacobian, and estimating it correctly is a key ingredient of the approach. To estimate J, what we have at disposal is an history of pairs delta Z and delta Y. Several techniques can be used, and in this work, we choose to illustrate with the Broyden update rule, but our method, we emphasize that it is not tied to this rule. What is important to note here is that delta Y and delta Z used in the update are defined with respect to an inertial frame, so that the shape Jacobian depends on this choice and is not independent on rigid body rotations. Once J has been estimated, we can use its pseudo-inverse and the shape error to obtain gripper commands. Usually, this error incorporates only the position error of the feature points. In our SE3-based approach, instead of using points as features, we propose to use mobile frames defined from the surface of the deformable object. The goal is now to control the grippers such that the feature frames reach a desired pose. This pose incorporates the position of the frame, but also a rotation matrix defining its orientation. HP is the current feature frame, and
think the video is stopped. Can we try playing it again?
Oh. Martina, are you still there?
I think there's some issues with her connection. So because Italy is far away, but we can just swap to the local version then.
There's a problem with the drive.
It's Windows, gonna work.
Oh.
So now we just need to share our screens. So it should be this one.
Yeah.
Hi everyone, I'm Guillem Alenyà and it's
We should share the screen here.
So
Yeah.
let's just share the screen.
Okay.
This both incorporates the position of the frame, but also the rotation matrix defining its orientation. HP is the current picture frame, and HT is the desired one. Now, since the shape Jacobian relates motion of frames, we need to redefine the Broyden rule. The key difference is that now we use relative transformations between the successive feature frames and use a logarithmic map to obtain the vector that we can use in the Broyden rule. We do the same for the gripper motions, and in the end, all the variables used in the Broyden rule are now coordinate independent and insensitive to regime volume motions, so that it will also be the case of G. Very importantly, we need also to redefine the shape error, so we use the relative transformation between frames HP and HD and the log map. Compared to the traditional approach, the error incorporates also rotation information. Again, we simply invert the model to obtain gripper motions, and we update them with either position or velocity control. To illustrate the results, we have made several experiments in the simulator bivalent. The controller has no access to the object model, and we initialize the Jacobian with null perturbations and finite differences. In the traditional approach, called here position-based servoing, we use 3 points shown in green here, and we use the same points to build the frame HP in our new approach. For small deformations, we observe that both methods work. However, the advantage of AC3-based servoing is more visible for high deformation tasks. Here, coupling position and rotation in the error avoids twists because it deteriorates the rotational part of the error. The trajectory we obtain is smoother and more straightforward. In contrast, for these two tasks, the traditional approach failed. Finally, when we subject the beam to rigid body rotation, we observe that in position servoing, the components of the Jacobian vary non-linearly, while in our approach, it remains constant, which should be the case, since the shape Jacobian should only capture shape variations. Finally, I would like to thank the ERDF that supports this research through the ICRA project. This is an interim project in the region Berenson that gathers partners from several countries to promote the development of composites in the region. To conclude, I would like to highlight that our approach is not tied at all to the Broyden rule, nor to the controller used here, so our method could be easily extended to other frameworks. Thanks a lot for your attention, and please do not hesitate if you have any questions.
Thank you very much. Any question?
We have questions on Slido, actually. The first question is, thanks for the presentation. Can you have more than one frame as the target in order to define more complex target shapes?
I speak
towards the laptop,
Maybe.
mostly loud.
Yeah. You can use several frames. Here.
Yeah.
You can use several frames. And in the case where the additional frames you add are near the gripper, it will in fact help in succeeding in the task, because the relation between the motion of your gripper and the motion of this frame will be, there will be a high correlation between both, and so it will help in succeeding a task. But if you define additional frames that are located far away from this gripper, then you have the under-actuation problem that will make it sometimes harder. So I would say to choose the frames, it will depend also on the task and on which points on your object you want to arrive at the good location. So it will depend on your task.
Thank you. I think.
Yeah, we can move on. But there's one more question about how do you determine the initial frame?
Yeah, but so it is related, but so it will depend on your task objective. If you are wanting to just bring some subset of your deformable object to some location, you will choose your inertial frame accordingly. I know it speaks about inertial frame.
Yeah.
Here it is independent of the inertial frame, the method, because it uses a relative transformation, so you do not need an inertial frame. But I don't know if it answers the question.
All right. So next speaker is Peter. I think, yeah, you should probably come up here and we'll play your video. Then if you have any questions, just ask as usual. You can take a seat here if you want. Or up to you.
It's like super silent.
We propose a data augmentation algorithm to increase data efficiency. Data augmentation can be used to great effect.
I think we need the volume.
In an image classification task.
It's as high as it goes. Sorry.
Is it better if I share? Now I'm back again.
Okay, try it.
This stupid laptop. Okay, let me try. It's quite silent anyhow.
And I'll be discussing our paper titled Data Augmentation. My name is Peter Mitrano, and I'll be discussing our paper titled Data Augmentation for Manipulation.
Okay, we're just going to have the presentation live. Do you want to talk over that or just without slides?
I'd rather than mute it so it's not confusing. Yeah, it's probably better. Or just play it on this side.
Okay.
Oh,
So,
okay. We can play it on this level, or we can just mute the sound and he talks over the slides.
Okay, cool.
Okay.
Now I'm starting.
All right. Hi, everyone. My name is Peter Mitrano, and I'll be presenting our paper titled Data Augmentation for Online Learning of Rope Manipulation. In this work, we propose a data augmentation method for increasing data efficiency for deformable object manipulation. Data augmentation has been used to great effect in computer vision, wherein, for example, an image classification task, we can sometimes apply random rotations or crops. And this has been shown in prior work to increase the data efficiency and generalization. But these methods are typically specific to both data type and task. And so while existing methods exist for text and images, the same cannot be said for robotics. In this work, we focus on augmenting trajectories of geometric state and action data. This includes object poses, joint configurations, voxel grids, or point clouds. We focus on short trajectories, and our method is applicable to both classification and regression problems. I'll now describe our method and then our experiments. So at a high level, we apply, we also go over the assumptions carefully in the paper, since data augmentations are typically very specific. At a high level, we apply a rigid body transformation to some of the objects in the scene. So we decompose the scene into three categories. There's the robot, the moved objects, and the environment. We frame augmentation as the following optimization problem with three terms: validity, relevance, and diversity. Validity means that the example obeys the laws of physics. Relevance means that it's similar to data you'd see when performing the target task. And diversity is maximized when the transformations are uniformly distributed. We take this abstract problem and propose a specific version for robotic manipulation, which has 6 terms. The first term expresses diversity as the distance to a uniformly randomly sampled target transformation. And the next four terms describe the validity and relevance of the object state. They enforce that the state remains within the workspace bounding box. They penalize invalid transformation parameters and preserve near contacts and contacts with the environment. The final term defines the validity for the robot state in action. We solve this optimization problem by splitting it into two parts. In the first part, we optimize the validity, relevance, and diversity of the moved object state. And in the second part, we optimize the validity of the robot state in action. I'll now go over experiments. So we start by evaluating on bimanual rope manipulation and simulation. The robot is holding the ends of the rope and is tasked with placing the middle under the hooks in the goal regions in purple. The planner here uses an imperfect model of the rope dynamics. And so in order to produce accurate plans, it learns a classifier that predicts whether the dynamics model is accurate. And we apply data augmentation to the training data for learning this classifier. If we analyze the success rates over the final 10 iterations of learning, we find that the method which uses augmentation has a success rate of about 70%, and the method without augmentation has a success rate of 48%. We also evaluated on bimanual rope manipulation in the real world. So the scene here is a mock-up of a car engine bay, and the robot has to move the rope, middle of the rope under the engine without snagging to set up for lifting the engine. Here we used CD-CPD2 to track the rope state with two Kinect 3D cameras. We ran 30 iterations of learning and then froze the models for evaluation. The evaluation found that without augmentation, it succeeded in 7 out of 26 trials, and with augmentation, it succeeded in 13 out of 26 trials. In summary, we propose a novel method for data augmentation for robotic manipulation. We formulate augmentation as an optimization problem, and we show that it improves performance on downstream tasks in the low data regime. Thank you.
Yeah, so any questions? Yeah.
Very nice work. Well, Trish, can you say something about the failure modes with augmentation?
Can you repeat the question?
Yeah, so the question was, what are the failure modes specifically with augmentation? So one way in which things could go wrong is you could produce augmentations that are invalid or irrelevant or just not diverse enough. So this is going to be probably most likely to happen when some of our assumptions don't hold. So let's say that the rigid body transformations don't preserve internal forces for some reason. So maybe gravity has a really strong effect or something like that. And in that case, you might produce data that is not either accurate to the real task or not relevant, in which case it wouldn't help.
What I'm getting is you have 13 out of 26. Correct?
Oh, I see. I think honestly, in this case, it's just that the amount of data is still, even with augmentation, small, and the task is really difficult. So I think while the augmentation helps, in order to succeed at this task 100% of the time, you'd probably need more than just 30 trials and more than just data augmentation. You need better control, better sensing, etc.
How is the robot represented with the state action space? Is it in Cartesian space or a joint space in the optimization?
So the question is, how is the state and action of the robot represented? So the state is the joint configuration, so absolute joint positions, and the action is relative gripper position changes. So move forward 3 centimeters in some robot frame.
We also have a question on Slido.
Okay, thank you.
That's how long is the time cost of the optimization to get a transformation?
Okay, it's fairly fast because we can do it in parallel on the GPU. We use PyTorch for the optimization problem. So we can generate anywhere between 5 and 15 augmentations per second. So it's pretty trivial compared to training time or robot execution time.
Okay, thank you.
Do we have time for one more question here?
Yeah, one is fine.
introduce a number of background parameters, like whether or not sensitive, whether did you have a lot of work to do or were you like roughly applicable?
So the question is, how sensitive is it to the hyperparameters and the optimization? It's not particularly sensitive. You could probably add 50% to any of the variables, and we didn't notice significant changes. The terms were chosen by basically just balancing the magnitude of the losses because they're in wildly different units.
All right, I think we should move on to the next speaker, but thank you very much.
Thank you.
So next speaker is Thomas. Thomas, are you, oh, yeah, do you want to come by here? We'll, Martina, do you want to play his video?
Yes, I'm playing it. No,
My name
wait.
is Thomas, and I'm going to
I'm
present a
restarting
paper.
it wasn't muted.
Hi, my name is Thomas, and I'm going to present our paper on learning key points from synthetic data for robotic cloth folding. Robotic cloth folding is a challenging problem due to its deformability, which results in infinite degrees of freedom. Nonetheless, complete pipelines for cloth folding have been created by leveraging the observation that it suffices to know the position of a few semantic key points or landmarks. These pipelines, although very impressive and robust, have limited potential to generalize to diverse environments, as they rely, for example, on segmentation techniques that assume a known background color distribution. In this work, we attempt to overcome these limitations by leveraging the generalization capabilities of neural networks. We train a neural network to detect towel corners and transfer this network to a real setup, which allows us to fold towels with a simple open-loop trajectory. By using procedural data generation, we can train this network without having to collect large data sets. We can also easily generate all desired variations in the dataset. Our pipeline contains three components: the procedural data generation, the key point detector, and the scripted fold trajectory. I will briefly introduce them in the next slides. To generate the training data for the key point detector, we create a 3D scene in Blender. We randomize the geometry and pose of the towel, as well as its material. For the towel material, we create a simple noise texture, as creating high-fidelity textures of cloth is time-consuming. The camera position is also randomized to make the network generalize to different camera poses. The major issue when training neural networks on synthetic data is the sim-to-real gap, or the decreased performance when transferring the network to the real world. To overcome this, we use domain randomization. We sample objects from the Thingy10K dataset to provide negative distractors. To introduce diverse lighting, we add high dynamic range images as environment maps. Finally, we add a random material to the surface to introduce spatial patterns. For the key point detector, we use a UNet-inspired architecture with residual connections in the bottleneck to combine spatial resolution conserving paths with a downsampling path for a larger receptive field. The network outputs a single heat map that contains all detected corners of the towel. After training on the synthetic dataset, the network achieves an average precision of 82%. We then manually define the grasp pose and the circular fold trajectory in a local frame on the towel. Once the corner locations are known, we can transform this local frame to the frame of the robot and fold the towel. To evaluate the system, we gathered 20 towels and divided them in two groups. Within distribution towels that have uniform textures as modeled in the synthetic data, and out of distribution towels that have unmodeled textures. The robot attempts to fold each towel under various circumstances. We change the towel's initial state, the environment lighting, and the presence of random objects in the scene. We use the grasp success rate to measure the performance of the key point detector and evaluate the complete system with a fold success rate. The system has a grasp success rate of 80% on the in-distribution towels. Grasp failures are due to wrong or incomplete key point detections, indicating that there is still a sim-to-real gap. In future work, we aim to further explore this to provide more insights and a more principled approach to procedural data generation. The difference between grasp and fold success rates are caused by limitations of an open-loop unimanual fold trajectory. In most failure cases, the corners of the towel get bent, resulting in a failed fold. For some towels, the difference in material properties causes the fold to fail. To conclude, in this paper we showed how to use procedural data generation to train a neural network to detect towel corners and use them to fold towels with an open-loop trajectory. This shows that synthetic data generation can be used to solve perception tasks for robotic cloth manipulation. You can obtain more information in the paper or by visiting our poster stands.
Any question? Yeah, I think you can ask your question here and then you'll just repeat it for the people on Zoom. Yeah.
Yeah, I have a question. So it seems that you have no texture on the cloth of the simulation data, but you have some real data using this seem to get this scenario.
Yes, so the question was about the textures that were used for modeling the cloth, where the textures in simulation were very simple and well, not really they didn't represent real cloth. And the question is, does this cause a sim-to-real gap? Well, I think that's indeed one of the things. I'll move away from this mic. So I think that's indeed one of the main issues with the reduced performance we saw. But the point is that if you want a diverse set of real textures of cloth, well, that's very hard to create, right? So this was the reason to use a low fidelity texture, but indeed it's causing the sim-to-real gap.
We also have two questions on Slido. So the first one is, can you use traditional methods like Airy's corner detection for detecting these corners?
Yeah, sure. That's a great question. I think indeed for the settings that we evaluated in this paper, you could use more traditional methods like the Harris corner method. I also quickly tried it and it did seem to work. Although we also, for example, experimented with adding some random objects in the scene. And once you start doing that, it becomes a little bit more tricky to tune things to make sure that these objects do not result in false positive corners. But yeah, with enough engineering, you could probably solve all these tasks. But the point is mainly that you can use this synthetic data also for more difficult cloth types because the methodology is not limited to rectangular shapes, for example.
Okay, thank you. Then we have, I think, the last question. That is, can the perception system be used to foreclose the loop folding?
Well, depends on the frequency of your controller. I would say the inference time for the network is rather small. So if your controller accepts control rates of 20 to 30 hertz, you could use that, I think. But then you would also have to train it on data where the manipulator is also in the scene because it would cause occlusions and stuff like that. So if you add this to the data, then you could surely use it for closed loop simulation as well. Maybe if there's still time, there was one question from the audience, but I don't know about the schedule.
Yeah, one more question.
You know, what fraction of real data do you think you would need to achieve the same performance? So say you had 100 samples of synthetic data, and then you collected, 10 very carefully, very careful samples of real data. Would that be sufficient to get the same performance?
That's an interesting question. I think sorry, yeah. So the question was, do you have an intuition on how much real-world data you would need? Like, what's the ratio between the simulated data and the real data that you would need to achieve the same performance? I think it depends on how well you choose the real-world data. Because, for example, I used, you have like the table of our robot is like an aluminum construction. If I would take the photographs all on that table, it would probably suffice to have like maybe 50 instead of 100 samples. But then it would only work on that specific table, right? And if you want to generalize to all kinds of tables, then it becomes more tricky and you would need more data. But I think you would need less data if you use real world data, obviously because you don't have a sim-to-real gap to overcome. But on the other side, that's more expensive to obtain and to label. But you would definitely need less data, yeah. Thanks.
All right, thank you very much. I think we should move on to the next. So we can move on to Irene video, and Irene is on Zoom.
Hi everyone, I'm Irene Garcia-Camacho and I will present you the cloth manipulation and perception competition. Establishing well-defined benchmarks that serve to evaluate different robotic manipulations is still a pending challenge in robotics. Several initiatives have been proposed in recent years, but a benchmark is successful only when it is widely accepted and used by the community. For this reason, during the last years, several competitions in robotic manipulation have been organized as a way to drive scientific progress in the field, as they enable comparison of different approaches with equal test conditions. One of them is the robotic grasping and manipulation competition that includes 3 tracks. Nevertheless, previous competitions have mainly consisted on rigid object manipulation, leaving behind the challenges that suppose grasping and manipulation deformable objects. For this reason, we created a new competition which will be held as part of the service track of this competition at ICRA 2022, which consists on perception and manipulation tasks involving highly deformable objects such as textiles. This competition is the first proposal to bring together researchers in solving the same tasks in cloth manipulation, comparing the different solutions in equal conditions. This comparison is now quite difficult to do with published works, as they use completely different metrics and use different types of objects. Another motivation of this competition is to increase the acceptance and use of the household cloth object set, which was designed as a first step towards benchmarking cloth manipulation through the standardization of textile objects, similar to what was done with the YCB object set. This set will be distributed to the participants in order to perform the tasks of the competition and will be able to keep it later to continue working with it. This competition consists on a small set of tasks based on the current challenges in 2 important areas of research in the deformable object, perception and manipulation. We selected 3 tasks that include problems that have already been tackled in literature, but that still require efforts to be considered as solved problems. The first task focuses on the main perception skills necessary for the following grasping of the textile object. It will be evaluated the ability of detecting relevant features and the selection of suitable grasping points according to the cloth configuration. Notice that this configuration is very important in manipulation, as it determines the possible grasps in order to manipulate it as desired. The other 2 tasks consist on the implementation of 2 of the most studied cloth manipulation tasks in literature. On one hand, the unfolding task consists on grasping a cloth and manipulating it until it is placed flat on the table. This task is considered successful when the cloth has been placed laying flat and is completely inside of the table. We also will evaluate the quality of the placed cloth by measuring the resulting area and computing the error. On the other hand, the folding task consists on folding the cloth 2 times once it's flat in the table. This task is considered successfully completed when the folds are performed according to the protocol and the opposing corners are together in each fold. In similar way to the previous task, here we will also evaluate the quality of the result. We selected tasks for both areas in order to allow people from both sides to have the opportunity to participate. In this way, with this competition, we are able to test separately the vision solutions, but also assess 2 common cloth manipulation tasks, which require of several manipulation skills that are also present in many other cloth manipulation tasks. We also allow to focus only on the manipulation part by easing the perception with the use of colors on the grasping points, for example. Besides, these 3 tasks together form a complete pipeline that can be executed continuously. Therefore, we offer a competition with a compromise between doing something that has been studied in literature and fosters research groups to participate, but also providing challenges with increasing complexity. We believe that the organization of this kind of competition is a great way to improve and compare state-of-the-art approaches, and that it will provide useful knowledge for the deformable object manipulation community. Thanks for listening.
Do we have any questions? Well, I
think Thomas has a question, right?
want to repeat that.
And I think Irene is not there, so I'm gonna answer. Oh, Irene is there.
Yeah, I'm here.
Okay, go ahead then.
Could you please repeat the question? Because here we couldn't hear it.
No.
Me? Do you want to repeat the question?
We need to repeat it inside.
Any of you.
So basically, the question, if I understood well, it was that we are relying basically on planar and kind of planar shapes, and there are more complex shapes like t-shirts that should be taken into account. Something like this? Yeah?
Why do you include rectangular shapes, closed items, and other measurements?
Yeah, that's the question. Irene, only why you are including only rectangular or planar shapes and not t-shirts?
Yeah. Okay. So as I said, this competition was made for distributing the household clothes set. This set is a first clothes set that only included household items that include different sizes and different shapes. But we are planning to extend this clothes set to other shapes and other items as clothing items with t-shirts, trousers. So in this set, it's not included, but it will be. Is that? Does it answer?
So Martina, should we move on to the next? I think we're running a little behind.
Yep. We also have a poster session afterwards in the break. So if there is additional questions, go to the poster.
But we have one more. We have one more video speaker. So Martina, do you want to?
Yeah, I'm sharing. Sorry. Okay.
We study a dynamic deformable manipulation task. We assume that the robot has already grasped the deformable object, and that the robot can accurately measure the 3D position of a single point on the object. Our benchmark task is to track a fast-moving trajectory with the measured point. The true state of a deformable object is continuous, infinite dimensional, and governed by complex dynamics. Furthermore, the system is only partially observable. We cannot measure the full continuous state from the real world, only the controls U and observations Y. We learn an input-output dynamics model from real-world data using a recurrent neural network, which has an uninterpretable hidden state, X. The recurrent network forms a discrete time dynamical system, so we can use standard nonlinear state estimation techniques to estimate a value of the uninterpretable state that is consistent with past inputs and outputs. In our protocol, we first interact with the object to build a dataset, which we then use to train the recurrent network. We estimate the recurrent network state from past inputs and outputs using an extended Kalman filter. We then use the mean of the Kalman filter belief distribution as the initial state for the dynamics rollouts in a nonlinear model predictive controller. The controller sets end effector, pitch, and yaw angles for the robot. The Kalman filter consumes inputs from the controller and measurements of a single point from a motion capture system. We test our method on a robot arm grasping a foam cylinder. This video shows the tracking performance for a circular trajectory. We also perform an ablation study where we remove the Kalman filter component. This results in an open-loop system with no opportunity to use observations to correct for modeling error in the recurrent network dynamics. The open-loop system shows degraded tracking performance. More details and the results for other trajectories are available in our paper.
Any question? Oh, you're on.
So there are no questions in the room. Martina, do we have some online? We lost just the Wi-Fi, so we don't have access.
We do have one question in the room in the back.
What's the motivation of this?
What's the motivation?
Everyone, can you repeat the?
Yeah. The question is, what's the motivation of this work? I think it's a great question. One of the initial motivations is trying to govern objects that are dominated by passive dynamics in sort of highly dynamical tasks. One of the initial motivations, which comes from a funding source, is manipulation in space. So if you have a very low power space actuator, so oftentimes you ship something up to the International Space Station, it has a very low actuator potential. You're manipulating maybe a cargo bag, and you have a very low actuation compared to the actual passive dynamics of the object. The test bed on Earth here is basically some task where you have these passive deformable dynamics that really dominate. So that's why we tried to make the task tracking as fast as possible. Thanks, it's a great question.
One more question? Yes.
And a follow-up. What is the motivation of using model predictive control for this task?
Yeah, what is the motivation of using model predictive control for this task? I guess my question there would be sort of as opposed to what? I mean, do you have something else in particular in mind?
Yeah, I mean that we can do something that does not require to have receiving horizon. We can minimize some instantaneous cost instead.
Yeah, it's a good question. I think because the dynamics dominate here and because there's some significant non-linearities in the dynamics, that's why we chose a nonlinear model predictive control architecture. There are other ways to solve this problem too. And future work, we'd like to benchmark against multiple approaches. Thanks. Yep.
How big was
Yeah, the question is how big is the data set when we train the LSTM? Thanks for your question. We actually only needed, I think it was about 10 minutes of data. We just rolled out some sinusoidal trajectories. One of the things that we found was surprising is we actually had pretty good task generalization. So we were able to track like a rectangular trajectory pretty well. Please stop by the poster. We have some results there too. Yeah, thanks for your question.
All right, so thank you very much. I think it's time for our first break. So we'll have a break right now, and please be back by 11 o'clock for our next speaker. So right now we have a coffee and posters, I think.
Yeah, so the posters are just outside the door. The people that post the posters, please hang them up on the poster session. The posters are just outside. And see you all at 11.